right, good afternoon, good morning, good evening, good day, whenever you happen to be watching this. So this is going to be part 3 of lecture 6 of ENGR 2302 Engineering Dynamics. All right, so I'm going to continue right where we left off in the previous video. Previously, I looked at developing the introduction to power, work, efficiency, but mainly kinetic and potential energy. So first, right off the bat, I'd like to work through a few practice exercises. So consider an example here. Let us consider an example. So let's say we have a car going down an incline. I'm going to have a car going down an incline. There's a car going down an incline. And an automobile, a car, basically this car weighs, so all this would be given. This angle is 5 degrees, so it's a fairly gentle slope, relatively. The weight of the car is 4,000 pounds. 4,000 pounds, and at a speed of, and it's traveling at 60 miles per hour. Traveling at 60 miles per hour. So it's going down so this car is going down a ramp or down a slope at 60 miles per hour. Then it will brake. Then brakes with a force with a constant braking force of 1,500 pounds. With force of 1,500 pounds. Of 1,500 pounds. And I'm going to determine, so all this was given here, and I want to find the total braking distance required. The total braking distance required. All right, so let's look at this. I'm going to evaluate using the model of work and kinetic energy. So this thing is going to come to a rest. Initially, it will be traveling at 60 miles per hour. And we're looking for a certain distance x that will cause this car to stop, that will be required for this car to stop. So initially, it has a velocity of 60 miles per hour. So v1 equals 60 mph. And v2 will simply be 0. And so then I could work with this. I want to transform these into feet per second from miles per hour. So v1 equals 60 miles per hour equals 60 miles per hour, which through simple unit conversion we can find equals 88 feet per second. Not difficult to do, just convert hour. There's 3,600 seconds in an hour, 5,280 feet in a mile. Fairly easy to get. And T1, the kinetic energy at 1, is going to be 1/2 mv1 squared, which will equal 1/2 times, I need to convert, now, notice I have the weight of the car. The weight is 4,000 pounds, but I need to convert this to a mass. So I'm going to do 4,000 divided by 32.2 times a velocity 1 at 88 squared. And the initial kinetic energy will be 481,000 feet-pounds of energy. Foot-pounds of energy. And then at V2, well, at point 2, the velocity is 0, so the kinetic energy will also be 0. Now, I need to relate work to this. And let's see, so I need to look at something here. Now, let's look at the, let's do a little free body diagram here. If I do a little free body diagram, if I consider the car just as a block, I'll have normal force pushing upward. Normal force pushing, sorry, not upward, but, and this will be our 5-degree angle. I'll have the normal force acting perpendicular to the force, to the displacement, so it will not generate any work. I'll have the 1,500 pound frictional force going opposite motion, and I will have weight pulling down, 4,000 pounds. And this will be going straight downward. This is also at an angle of 15 degrees from the, also at an angle of 5 degrees from the vertical. 5 degrees. So if I work through the trigonometry, I can find the work, again, just taking the component of each, the only two forces that can do work are the gravity force here, the weight, and the frictional force, again, because of the components, and we're looking for the component of each of these that is going to be non-parallel, or non-perpendicular or parallel to the displacement. So the U, the work from 1 to 2, will be equal to negative 1,500 pounds times x plus 4,000 pounds times the sine of 5 degrees times the sine of 5 degrees times x, which will equal negative 11,511 pounds times x. All right, continuing on. T1 plus U from 1 to 2, the work from 1 to 2, so the kinetic energy at 1 plus the work from 1 to 2 will be equal to kinetic energy at point 2. And so this will be 481,000, that's a really bad 8, 481,000 foot-pounds of energy minus 11,511 pounds x, 5,011 pounds, let me put a little dot there, 11,511 times pound times x, all of this equals to 0, the final kinetic energy is 0, and we can find that x, the braking distance, will be 418 feet. 418 feet. So let's sit back and think about this for a second. Well, what we can see here is that this car, we found the total distance it takes to brake. What we did not find, however, was the acceleration. If we wanted to do that, we would have to look at Newton's second law or some other form of analysis. Again, I keep coming back to this, the methods of energy, they're time independent. We're looking only at the distance, the forces, that sort of thing. We're not actually looking at the time for something like this to occur. So because of that, we don't know the accelerations, we don't know those things directly. We would have to use Newton's second law in order to determine them if that's what we wanted. Okay, so let's see. And that's kind of the same idea here. And we could work through some more problems like this, but the basic idea is the same. All we're going to be looking at is problems of work, energy, balancing them, balancing kinetic energy with other forms of energy, etc. Okay, so we could look at other connected systems, but I think this is fairly straightforward. So maybe I'll work through another example. Example 2. I have a, let's say I have something like this. So I'm going to have the ground and a rigid wall here, and then I have a crate that's flying along at 2.5 meters per second. So this is going to be a 60 kilogram crate. And initially this thing is flying along at 2.5 meters per second. 2.5 meters per second. And I'm going to put a spring here, just for fun. I suppose that'll work. Why not? A spring here. And this spring is attached to a plate, and then the spring is attached to, there are also cables giving the spring an initial compression. For whatever reason, We want to be able to generate a large amount of force at the start. So all of this is given. The K of the spring constant. The spring constant is going to be 20 kilonewtons per meter. And the cables, let's see. So again, there's cables here and here. So the unstretched length would be something like out here, but I have cables here and here that are going to provide an initial compression. This isn't the initial length, but an initial compression. An initial compression of 120 millimeters. Let's see. And I'm also told that the max deflection of the spring is 40 millimeters. Is 40 millimeters, so it's going to compress from, let's see, 40 millimeters. 40 millimeters here. Let's see, just 1 second here. 40 millimeters. And let me just take a look at this here. Yeah, that makes sense. Okay. Okay, and deflection of the spring, what I want to be very clear what I'm talking about. This is going to be the change from initial position. Change from initial position. So in other words, when I'm saying deflection in this case, I'm meaning the change from the initial position. So basically the spring is going to start out compressed 120 millimeters, and then it will compress an additional 40 millimeters after the package hits it. And when it has a speed of 2.5 meters per second, it is exactly 600 millimeters to the plate. And the reason that's important is that this surface is not frictionless. 600 millimeters. And just for fun, this thing isn't frictionless. So all of this is given. And then I want to find a few quantities. So find, let's do A, the coefficient of kinetic friction, the mu kinetic, between the package and surface, between the package and the surface, and B, the velocity as it passes back through the initial position. The velocity as it passes back through the initial position. Back through the initial position. Back through the initial position. Okay, so again, it's going to fly along here. It's going to strike the plate. That's going to cause the plate and the spring to compress. And then once it reaches a maximum deformation, it will spring back the other way, and it will accelerate the package again. And I want to know the velocity as it's passing back through the original point. Okay, so let us compare two different things. I'm going to do a T1, T2 analysis looking at, so I'm going to let T1 be the initial position shown on the previous diagram. The initial position. and T2 be the point of full compression. So T1 will equal 1/2 mv squared. That's the initial kinetic energy, 1/2 mv1 squared, which is 1/2 times 60 kilograms times 2.5 meters per second quantity squared, which is then equal to 187.5 joules. And T2, the kinetic energy at point 2, is going to be 0. And then if I look at the work from 1 to 2, U from 1 to 2 is going to be, well, let's think about this here. U from 1 to 2, let's see here. Well, it's going to be essentially the frictional force times the distance, times the displacement. So this is going to be the work done by the frictional force. And let's see then. Now, let me think. I might need to define this a little better. No, that'll work. Okay. Here, just a... Okay. Oh, sorry about that. Okay, I'm having some technical difficulties here. Okay, there we go. Okay, so the U from 1 to 2 of friction, so I'm going to need to do two different work calculations. The work from 1 to 2 of friction is going to be negative mu kinetic times the weight of the package, because normal force will be equal to the weight of the package in this case, so it'll just be weight here. So that's going to be negative mu kinetic times 60 kilograms times 9.81 meters per second squared times 0.640 meters. So U1 to 2 will simply be equal to negative 377 joules times mu kinetic. P min, this is going to be the work, basically P, I'm going to let P be the package force, or the spring force. So basically we have a force P as, this is the force produced by the spring that is going to decelerate the package. So P min is K x naught, the initial position, the initial displacement, equals 20 kilonewtons per meter times an initial compressed length of 0.2 meters equals 2,400 newtons. And then times equals 2,400 newtons. P max equals K times x naught plus xo, plus delta x, x naught plus delta x, the initial compression plus the change in compression. So that's going to be 20 kilonewtons per meter times 0.160 meters. And this is equal to 3,200 newtons. 3,200 newtons. And so therefore, if we consider this, if I look at the force diagram of this, so I would have something like, if I look at a force diagram, so if this is P and X, I have P min here. Because of the cables, the force in the spring is never 0. And then this is delta X equals 40 millimeters. Equals 40 millimeters. And moving on, oh sorry, the reason I drew this out is because The work done by these forces, or by the spring force, is again simply going to be the area under the work force diagram. So this is the U from 1 to 2. And I'm going to call it the U from 1 to 2 E for elastic. And so let's calculate that. Just going to be the area of a trapezoid. U from 1 to 2 for the elastic or spring deformation is going to be -1/2 times P min plus P max. P min plus P max times delta x. So that's going to be -1/2 times 2,400 newtons plus 2,400 newtons plus 3,200 newtons plus 3,200 newtons times 0.040 meters. And this equals -112.0 joules. So we noticed in the previous case here that, well, let's see, let's look at the work here. The work here was negative, and the work here is going to be negative, because both of these are going directly towards slowing down the package. So it shouldn't be surprising that these are both negative. -112 joules. And so then I can just do T1 plus U1 to 2 equals T2. And so, moving along, I can do, let's see, well, T2 is going to be 0, and so that just goes to 0. But I can put in the components of, for T1, it's 187.5 joules, and U from 1 to 2 is made up of the two work components, the work produced by the two forces, both the friction and the spring. 175 joules times mu kinetic minus 112 joules is equal to 0. And we can quickly see that mu kinetic, if we solve for mu, is going to be equal to 0.20. The coefficient of kinetic friction on the surface will be 0.20. Next, I wish to find the rebound of the package. Okay, so I need to look at a free body diagram of the package. This time, there's going to be a different free body diagram. And I'm going to have P, force P, the pushing force from the spring. And now friction is going in the opposite direction. So this is F friction equals mu kinetic F normal. This is F the normal force, F normal, and weight, or force of friction will just be mu kinetic times the weight. So I'm going to have T2 and T3. Here, T2 is point of max displacement, of max spring displacement. T3, or position 3, is where package rebounds. Back through initial location. So let's see, T2 is going to be equal to 0 because there's no kinetic energy there, because it's stationary. So T3, though, will have some energy. It'll be 1/2 mv3 to the third, or v3 squared, which equals 1/2 times 60 kilograms times v3 squared. 60 kilograms times v3 squared here. Then U from 2 to 3, will be equal to U 2 to 3, the work 2 to 3 done by the elastic force plus the work from 2 to 3 done by the frictional force. Actually, I'm going to put the frictional first, plus the elastic force. So that will be negative 377 joules times mu kinetic. See, it's going to be the exact same one as the other one. I don't even need to bother calculating it. Well, yeah, because the same amount of work will be lost as the friction doesn't change. And the spring just gives all the energy back that it got originally. So that's 112 joules. And this comes together to equal 36 plus 36.5 joules. So then T2 plus U2 to 3 is equal to T3 is equal to T3. So 0 plus 36.5 joules equals 1/2 times 60 kilograms times V3 squared. And from this, I can get that V3 is equal to 1.103 meters per second. 1.103 meters per second. Okay, and that's the basic way these energy exchange problems work. You look for the work along certain distances. You look at the potential paths. You balance the kinetic energy with the work, and solve through from there. And you do pay special attention to the and you do pay special attention to the direction of forces to see whether they will have a work component associated with them or not. All right, so let's continue on, see how far we can get today. Let's see, just going through some notes here, seeing exactly what I want to cover. Okay, I'd like to sort of finish up this 6th lecture with a discussion on potential energy. There are definitely more examples I could work through with basic energy methods, but I think you kind of get the idea. Okay, so what is potential energy? We've hinted at it before, but I think I might explicitly spell it out. That might be beneficial. So what is potential energy? Well, potential energy, one way to think of this, is the work of the force of gravity. It is the work of the force of gravity. Work of the force of gravity. Force of gravity. W vector. Okay. If we consider gravity the W vector. And so say I have a object that is going on a path, and it can be an arbitrary path here. So it starts out maybe at A1 here, goes up to A2, and then in the middle somewhere at any given location A, there is going to be the force W acting on it. Or sorry, the force, no, that's right, the force W, the weight of the object itself acting on it. And then some dimensions here. Let me put some dim lines on this. I would have Y1, I would have my generic Y, just at a particular A, and then I would have Y2. So, U from 1 to 2 will be equal to, okay, so let us look at the work that is done on this, done by gravity, or done by the weight from 1 to 2. Well, let's think about this. So we know again that work only occurs if there is displacement displacement parallel, either parallel in the same direction or displacement in the opposite direction. That is, so work only occurs if the force is parallel to the displacement. Now, I shouldn't say it has to be parallel, but it has to have at least one component in the parallel direction. And that works just fine for gravity here. So the whole weight, the whole path will not generate work, but the vertical displacement will be important. So the horizontal displacement will not factor into the work done by gravity. However, the vertical displacement will. So this is going to be equal to Wy1 minus Wy2. The weight at point 1 times y1, the displacement at 1, minus w times y2. Or, let's see, I'm going to define the gravity, the variable v sub g, where v will be the potential energy, and this is going to be basically potential energy at a point is w times y. So v sub g is the potential energy of a body. Let's say the potential energy of the body with respect to the force of gravity. Of a body with respect to the force of gravity. With respect to WRT, the force of gravity. And if I compare two different points, I would have the u from 1 to 2 equals v, vg on 1, vg at 1, minus vg at 2. And I mentioned the term datum in a previous portion of this lesson. And again, the choice of datum, though, will be arbitrary. Choice of datum is arbitrary as long as you're consistent. Is arbitrary. All right, and so the units then, the units of this will be the same as potential energy, work, etc. The units Vg, if we look at this, are W times Y, which will equal Newton meters, Newton times meters, or simply joules. It's a unit of energy. It will have joules. Okay. So, now if we look at something in greater detail, though, what I went through previously, the previous formula, only valid is only valid if the weight is considered constant. But gravity doesn't tend to work that way, at least over long distances, if the weight is constant. So if you have something in space or moving at a significant fraction of the Earth's radius, or any body's radius, in space, variation in gravitational strength is large. Is significant. So, instead, I would have something like, if I used the gravitational force formula, if I compare two different points, I would find that the u from 1 to 2, if I could run through a whole diagram and everything, but the basic idea using gravitational force at comparing two different points, R1 and R2, just two different displacements, with R being the distance from the center, would be G M over R2 minus G M over R1. And so, with that, then from this I can get the potential energy. So the potential energy Vg, when variation of gravity cannot be ignored, so not near the Earth's surface, in gravity cannot be ignored, well, this would be Vg equals negative G mm over r, or negative W r squared over r. Negative W r squared over r. Let's see, negative r squared over r. Now, let's see that. I need to find out what that capital R is for you. Here. Actually, no, that seems to be a typo in these things. This should be, well, it's just negative G mm over r. Well, I could say that mass is going to be, if I said G, well, maybe that's just that's the variation of, that's the body or whatnot, the body velocity or something like that. Let's see, I don't know if I necessarily like that one, though. In fact, you know what, I need to research what that capital R would be, so let's just ignore that one. Negative G mm over r is probably the one you want to use in general. Now, the question is, though, why is this negative? You might be asking yourself that. See, this can be a bit confusing the first time people see this. See, people are used to seeing the potential energy as positive. If I go to a higher elevation, the potential energy would be tends to increase. If I go to a higher elevation, the potential energy tends to increase. So, you know, if I'm standing on top of a mountain, the potential energy should be higher than if I'm in the valley floor below. And if you work through the math, you'll find the same is true here. If I look at a larger radius, this number becomes less negative. However, it's always negative. No matter what r I put in, I always end up with a negative number. So this is taken with Vg equal to 0 at infinity. And this is very common in physics. So in other words, the potential energy is considered 0 at infinity. And the reason for that is if you had a body like the Earth and an object arrives from very far away, actually we define it as at infinity because that's basically at the location where the gravitational force is 0. Where gravitational force is 0. And so as this thing falls in, as a particle falls in, it's going to accelerate. So as this thing falls into the Earth, it's going to accelerate. And in fact, maybe I'll just draw a series of velocity vectors. Velocity, 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 etc. As this thing falls in, the velocity gets larger and larger and larger. And where that's coming from is from the gravitational potential energy of the particle. So something sitting on the surface of the Earth is in what we call a gravity well. You've probably heard this term before. Gravity well, it's just like being at the bottom of a deep well. All of the mass that is on the Earth's surface ultimately fell in there, either relatively recently or during the creation of the Earth or whatever. It fell into a gravity well. And as it fell, that energy was liberated in the form of kinetic energy. And later, that ended up as heat. It was the object when it struck the Earth that later became the atoms of the Earth were simply absorbed into the overall body of the Earth, and that contributed to the Earth's overall mass energy, etc. A lot of that heat energy was later gets vented off into space, etc. There you have it. So when I say that, this is why potential energy is negative. Potential energy is negative because every object is inside a gravity well, or are inside gravity wells, multiple. Potential energy is negative because of gravity wells, because they are trapped in gravity wells, because objects are trapped in gravity wells. And that energy had to be paid. Energy was released in order to get them down here. And so they've already released their energy. They've already released their potential energy. And if you're going to lift something out of the Earth's gravity well or lift it into, say, solar orbit, you have to apply a tremendous amount of energy to it. You have to lift it out and apply you have to basically pay the price back that was originally given when the thing fell into the Earth's gravity well. So that's gravitational potential energy. And I'll also mention spring potential energy. Although I think we've looked at this a bit already. This is just the spring potential energy. You can derive it fairly easily based off of a force mass or a force distance diagram of a spring's force. But we can see another way to think of it is simply VE, or the final derivation of it, if you want to work through that, is VE equals 1/2 k x squared, where x is the displacement. Or I could say, this is based on the idea that the work to go from 1 to 2 is just VE, the spring potential energy at 1, minus the spring potential energy at 2. So the spring potential energy at a particular point is 1/2 kx squared, and the work to go from one to the other is the subtraction of the two spring potential energies. Okay, and then finally, I think I might like to define the idea of a conservative force. Actually, I think I may need to put a final part 4 of this lecture. I'm kind of making this one in bits and pieces through the week, but I think I'm going to need to record the final 4th piece of this lecture number 6 a bit later. So that'll do it for tonight, or that'll do it for this portion of the lecture. Thank you for watching, and as always, thank you.